Okay, question number 6 on page 640 says a single isolated proton is on a fixed surface. Where must another proton be located in relation to the first in order that the electrostatic force of repulsion would just support its weight? So we're looking at this top one, okay? And so if we look at the forces acting on this top one, just like I said in class today, there will be an Fg acting down and an FQ, a force of repulsion, acting up. And if the force of repulsion is supporting the weight, it means that when you do the sum of the forces in the y direction, it should be 0. So that means FQ minus FG will equal 0, or K Q1 Q2 over R squared should be equal to mg. And they're both protons, which means the q's are the same. So kq squared over r squared will equal mg. Just moving it up here. Then, and we're looking for r. Where should it be placed? So that means r squared will equal kq squared over mg. It's a proton, and the other day I gave you the charges and the mass for a proton. So K is 9 times 10 to the 9th, Newton meters squared per coulomb squared. The charge on a proton is 1.602 times 10 to the negative 19 coulombs. Whoops, I just went off the sheet. And that has to be squared. The mass of a proton I also gave you the other day, 1.673 times 10 to the negative 27 kilograms. And of course, G is 9.81 because we are at or near the surface of the Earth. We're not doing this on the moon. Okay, so you punch these in your calculator. You get an R squared, and then you are going to take the square root. So R squared is 1.4074 to the negative 2 meters squared. Take the square root, 0.1186 meters. So they have to be like 11 centimeters apart in order for their force of repulsion to support the weight. So that was number 6. Then I asked you to do number 8. And you should be thankful I told you you could skip number 7. Tonight I'm going to get you to do part of number 7, but I won't make you do it all because it's rough. If you have to do it all, it's long. So this charge up here is minus 5 microcoulombs, excuse me. This one down here is positive 3 microcoulombs, and this one over here is negative 6 microcoulombs. Okay? And this one is number 1. This one, which one is number 2? I can't even see. This one is number 2, and this one is number 3. And the question, and this is 0.2 meters, and this is 0.16 meters. And the question wants to know what is the, okay, so charge A, I called it 1. I'm on number 7. What is the net force on Q1? So what is the net force on this guy? So you're going to do FQ12, which will equal KQ1Q2 over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared. Q1 is positive 3 times 10 to the negative 6 coulombs. Q2 is negative 5 times 10 to the negative 6 coulombs. And the distance between these two is 0.2 of a meter squared. So punch this in your calculator, and you will get a Q1, Q2. Oh, did I just do the wrong one? Can I not see? I can't tell which one's Q1 and which one's Q2. This is 5, sorry. So this is 5. Oh yeah, I did 5, okay. And when you do this, you get negative 3.375 newtons. So then you do, that's Q1, Q2. So then you, and the negative, of course, means force of attraction. So then you do Q13, and that's KQ1, Q3 over R squared. So 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q1 again is positive 3 times 10 to the negative 6. And this Q3 is negative 6 times 10 to the negative 6 coulombs. And the distance between them is 0.16 of a meter squared. And when you do this, you get Q13 to be negative 6.328 newtons, where again, the negative is attraction. Okay? So now we take a look at number 1. Oh, and this angle is 54 degrees. So on number 1, there is a force going up this way because it's attraction, so number 2 is attracting it. So this force is 3.375 newtons. And so it has 2 components. This was F12. So it has a component, 54 degrees, it has a component F12x and a component F12y that we're going to need to find. And then Q3 is also attracting, so Q3 has a force also going this way because it's attracting of 6.328 newtons. So before we can find our total, we need to find our 2 components. So F12y is going to be sine, so it's going to be 3.375 newtons times the sine of 54. And F12x is going to be 3, sorry I didn't rewrite that. It's going to be 3.375 newtons cos of 54. So your next step is to find the components. So the y component is 2.73 newtons, and it's going up. And the x component is 1.98 newtons, and it's going to the right. So our total in the y will just be 2.73 newtons. And our total in the x, because they're going the same way, will be 1.98 newtons plus 6.328 newtons for a grand total of 8.31. Yeah, 8.31. I think I probably rounded. I'm using the numbers. Yeah, it's really 8.308. I probably kept them all in my calculator, but I didn't round them all. So this one is up, and this one is to the right. And so then you draw it. So to the right, we have a rather big 8.31 newtons with your decimals in your calculator. 2.73 newtons, and then in the end, this is the force F net on number 1. So you're going to square them, add them, take the square root, and find the angle. So when you square them, add them, and take the square root, you get something like 8.749 newtons at an angle of 18.19 degrees, and that will be CCW positive x. It's upward from the positive x. Okay, so when you have something at an angle, find its components, then add up all the forces in the x, add up all the forces in the y, and then do the Pythagorean theorem in the angle. So that is number 8. Number 9 is not nearly as bad. And we're going to run out of time. So on number 9, it says you have a string with a pith ball hanging here. And a pith ball is like a tiny little piece of almost styrofoam. It's really light, okay? And we're giving it a charge, and then we're bringing a second one that is charged the same way in near it, okay? And when we bring it in near it, this one's going to repel. And because it's on a string, and then it can move up like this. And then it stays there. So this guy swings up, and so now it's up here. So in my new diagram, this one is here, and this one is here. Okay, and it tells us that this angle